All right, well, thanks for organizing this session and having me here today. Sort of the motivation for this work was some of the early studies of the Galilean probes to look at the Galilean satellites, which noted that below the outermost layer of ice that exists in these planets, there is likely a solute-rich fluid. Now, there's a lot of data suggesting that we can't get a lot of these solutes into the outermost ice layer, but that what we can do is potentially get those solutes from this fluid layer into the higher pressure ices as we go deeper into the planet. So the motivation for this study is basically, is it possible for this fluid phase, which has dissolved solutes, things potentially like sodium and potassium and chloride, to end up in either of these icy layers? And so that's really what we were going to try to do in these studies, is to evaluate this. Now, there's been quite a bit of work in the last 8 years or so on this sort of topic, where we've looked at the amount of solutes such as sodium chloride that can go into ice 7 predominantly. The ices at high pressure, we transition from fluid phase to at about 0.9 GPa into ice 6, and then about 2.2 GPa you transition into ice 7, and you have some structural changes with the ice at those conditions. So there's been quite a bit of work of what would happen if we could incorporate sodium and chloride into the ice structure, lithium chloride as well, and then molecular impurities, ones that don't dissociate in the fluid, things like methanol. Things like methanol, and then compare that to pure H2O as well. So essentially always coming back to pure H2O to see what effect the solutes have on the ice structure itself and the volumetric properties. And then at higher temperatures, and there hasn't been a lot done on the high temperature side, just a couple of studies on Jornox and then the Frank et al. 2008 study, is what impact do these solutes have on the melting curve of ice 7? Can it be depressed? And that's what they found in those studies. So for this study, we wanted to focus on potassium chloride, which would dissociate in the fluid. Then we would seal it in as potassium plus and Cl minus into the structure at high pressure to see what impact that had on the crystal structure. We did potassium chloride because it corresponded very well with sodium chloride, and we were then able to increase the temperature on these systems to see what impact that had on the melting curve. So potassium was utilized for a couple of reasons. One was it's a very close analog to the NaCl system, so we wanted to see how changing the cation size might impact the volumetric properties. But we also noted that potassium, which has a radioactive isotope, potassium-40, if we could incorporate some of this potassium into the ice, then we could actually make the ice layer not just a conductor, but a source of radiogenic heat. So we were trying to evaluate, could the impurity be put in, and then what would be the sort of geophysical implications of that. So these are experimental studies. They're not models. We're not going to go up to 700 gigapascal. We're going to stay at the sort of low pressure side of around 40 GPa and less. So the first thing we wanted to do was see, could we get at room temperature sodium or potassium chloride into the ices. So we did the experiments in symmetric diamond Anvil cells with culettes of about 450 microns. That's this dimension from there to there. We would pre-indent a gasket. In this case, it was mostly stainless steel for the low temperature runs to about 30 microns, and then we would drill a sample chamber in the middle, which is about 150 to 175 microns. Seal that in there, put in the gold, which is our pressure calibrant. I'll talk more about that in a second. And then put in the fluid. And the fluid was a 1.6 mole percent KCl aqueous solution. We utilized that composition because it corresponded to the work done by Frank et al. In 2006, 2008, where they looked at how sodium chloride, what was the maximum solubility of sodium chloride in this ice 7, and then the impact. So we were able to compare directly to the sodium chloride system, which is why we utilized that. So this would give us a compression curve at one temperature, at room temperature. And then we did high temperature runs using a hydrothermal diamond Anvil cell, a different type of setup. The same basic loading phenomena. We basically put in a solution with gold for our pressure marker. And then we could actually heat the diamonds themselves while measuring their temperature, and then be able to evaluate how the ice's volumetric change, or excuse me, how its volume changed with increasing temperature, and then ultimately could it melt, and what was the impact of the potassium and the chloride on the melting. So we had to do these experiments at a synchrotron because of the low Z material and the very thin samples required in a diamond Anvil cell. The experiments were done at Argonne National Lab, GSE CARS 13 BMD beamline. We use the X-rays for a couple of reasons. One is that we use that to actually be able to evaluate the phases that existed in the sample chamber to see if it was just ice 7 or if we had other phases as well. We use the X-rays to interact with the gold, use the equation of state of Anderson et al. To be able to get a pressure from that property. And the beam size is small enough for our relatively large sample chambers that we can move around the sample chamber, evaluate different parts of the chamber to make sure that there was no new phases in there as well. We utilized angle dispersive X-ray diffraction techniques because that would give us high precision values in a large reciprocal space in D-spacing. So this is the typical diffraction we would see from these types of studies. So this is of ice formed from a 1.6 mole % KCl solution. Intensity along the y-axis and then d-spacings here along the x-axis. The phases are pretty simplistic. The outline here, the ones that are listed in black, those are the diffraction lines for gold. And again, we use those to be able to calculate a pressure using the volumetric properties. And then the other phases that are outlined here in blue are just the ice 7 phase with the included potassium and the chloride in that phase. So we don't see, at room temperature, we don't see any KCl, we don't see any mixed phases, we just were able to put that much KCl into the phase, into the structure. So at room temperature, we would then take a sample, increase pressure, take another X-ray diffraction pattern, and so every black dot here is one of those PT points as we go up in pressure up to a little over 30 GPa or so. When we compare these results for pure H2O, this is in the blue curve here, we see that the volumes are systematically reduced relative to volumes we would expect for pure H2O. There's a black line underneath here. That's our equation of state that we fit to. This is the zero pressure volume, the bulk modulus, and the pressure derivative, and you can see the relative fit there. The red line is from the Frank et al. Study, which was for NaCl formed inside the ice 7, and you can see that the same molar percent, it's basically the same curve. So both NaCl and KCl seem to do the same thing in the ice phase, and that it basically actually decreases the volume, which is kind of interesting. We're putting an impurity in, but we're actually decreasing the volume. Now, when we consider the fact that we add impurities in addition to reducing the volume, we're actually seeing a density increase in these ices of about 7%. Just to put this into context, when we actually look at subduction zones here on Earth, we're looking at a difference in density of about 10% if it's continental versus oceanic material. So this variation in the solutes that can go into the ice may be impacting the way that ice can move around and be recycled in some of these larger planets. Now, when we focus in here, you see that as we get to the lower pressure realm, which is going to be the more shallow portions of the system, we can see the relative difference here. So yeah, although that this seems to, and when we look at the large pressure range, it seems to be pretty well packed together. There is a pretty significant difference there. So our sort of working hypothesis for the last 8 years or so on how this really occurs is that the ice 7 phase is the BCC, or body center cubic phase, and the results by using Raman and some other ideas is that we can actually take the potassium and the chloride, which is what exists in the fluid when we pressurize it to ice 7 pressures, that we're probably trapping those in the face center cubic sites. And then when that happens, the H2O molecules will actually rotate to accommodate those, and that will actually end up pulling the structure in on itself. So we actually reduce the volume in that method. So the potassium comes in, and then the oxygens will rotate to coordinate with that, and then when the chloride goes in, the hydrogens will rotate around to coordinate with that, and so we're essentially making something that's kind of like an ice 10 style structure in that case. Well, room temperature data are great. It gives us an idea of what's going on in the system, but to really understand the evolution of these planets and what exists in their interior, we have to also increase temperature. So the hydrothermal diamond cell experiments were utilized where we would compress the sample to a target pressure and then heat. So what we have here is that diffraction line down here where, again, all we see is the gold diffraction lines, which are outlined in the black, and then the blue ones here, the noted, those are for ice 7 there, and then we're going to have another one out here. So while we're at that target pressure, we would heat up the sample, and from 350 degrees C, all we were able to observe is some slight variations in the unit cell parameters as we're expanding out the unit cell with increasing temperature. But then as we hit 400 degrees C, we started to see diffraction lines here and here, which are actually indicative of KCl, the beta phase of KCl. So as temperature is increased in these ices, we're actually exsolving out KCl. So this is, from a geologic perspective, kind of unique because usually as temperature goes up, we increase entropy and we get more mixing, but in this case, we're seeing the opposite thing. This has been observed for NaCl systems as well, and going back quite a bit, it actually was observed in the nicotine water system as well. So it's kind of a unique phenomenon. So as temperature went up even further, we got to 475, we see the KCl peaks disappear. We see one ice peak that's very sharp out here. That's probably because at that condition, we initiated the X-rays as soon as we got to 475 K, and that we actually are observing melting. As we let that experiment run just a little longer, we didn't increase the temperature anymore. The ice peaks went away, the KCl peaks were gone, so we know that melting occurred somewhere between 450 and 475 K in this case. So we're able to utilize a couple of these heating cycles to be able to constrain the volumetric changes in the ice with KCl and also the melting curve. Oh, sorry. So this is our equation of state. I'm not going to spend a lot of time on this, but we basically have, we conducted it at 50-degree C increments or 50-degree increments coming up. This is the volume that we observe versus relative to 300 K, and you can see the expansion. So the equation of state fits pretty well. So we can use our values to be able to fit what happens with the volumetric properties of the ice as we go deeper in the body. And now comparing that to the melting curve, it looks something like this, where we have ice-only diffraction lines here, and then the green represents where we have ice-7 diffraction lines with some KCl through exsolution, and that these open sort of boxes here are where we have midpoint data. That means that at one pressure we have, let's say here we have ice-7 plus KCl, and then we decrease the pressure in the system, and then we end up with the fluid. So we use the midpoint between those two as a melting point, and then we use the midpoints that we have and the Simon-Glatzel equation to calculate a melting curve, which we have the data for. I didn't put the numbers up here for the parameters, but that's it. And then when we compare that to pure H2O, we see that there's a pretty substantial drop in the temperature of melting by adding the KCl, but it pretty closely relates to the NaCl system, although there's a deviation here as we get the higher pressure. And that's just because I think we have a little better data here for the KCl system than we did the NaCl system. So the incorporation of these ionic impurities are actually depressing the melting point of ice-7 pretty substantially at these pressures. Now, what is the implication of all this? If we go just to the density information and the variation in density, we can sort of look at sort of a large planetary body where we'll sort of have schematically a metal core and then a rock outer layer. But if we've got a fair amount of H2O in the system, we'll have an outermost ice shell, and then we'll have a low pressure ice plus fluid. Now, if we can get these ionic impurities into the ice, either through interaction with the rock layer or through interaction with this fluid which contains solutes, we're going to end up with sort of a stratification that may look something like this, where we have ice-6 up here, which we do know we can have some impurities in, but probably not a substantial amount. Then ice-7, which has got low impurities. As we go to impurity-rich ice-7, that's more dense. That's going to go deeper into the planet. And then as we go to higher temperatures, we're going to exsolve some of that KCl out down here, where we're going to have KCl here. And so we can end up with essentially a stratified body that looks something like this. Now, adding potassium also adds heat because of the radioactivity of potassium-40, so we can actually make this layer a thermal source or a radiogenic heat source, which then we can have heat flow coming up to the shallower portions of the body. So we're not just restricted to heat coming from the rock or the metal core, we can actually have heat coming from the ice layer. Now, when we consider all of this together, the differences in density, melting, exsolution, all of these are mechanisms that could result in, at least in these large icy planets, ways that we can actually encourage differentiation and segregation inside the planet itself. And so you could certainly imagine that the difference in density might be enough to drive a slab down to deeper parts of the system, that the increase of potassium, the radiogenic heating could induce melting at the lower temperatures we see in the potassium system. We could generate a plume that comes up into the fluid layer, and then we can start the whole process over again. Now, in addition to these ideas about potential differentiation, the fact that we do have salts at either these ionic impurities, KCl or NaCl at depth, could also indicate that we could have some weak planes down there where we could actually get sort of solid state flow as well, even if we're not in the melting zone. So just by adding these impurities, we can do a whole lot of different things in the planetary structure and lots of arm waving that needs some more extensive modeling. So the summary is that there's been quite a bit of literature work and shown that we can incorporate these impurities, both ionic and molecular impurities, into these ices. So these systems are probably much more complicated than pure H2O. And that when we do that, we can depress the melting curves, we can have differences in density, we can drive exsolution, we can do lots of things in the planet, as well as provide a heat source when we bring in potassium as well. So I'll take any questions. Thanks.
So one quick question. Dave?
You seem to be using quite high potassium abundance, given that there are other places to put potassium, for example, the rock component. Often when people talk about oceans in the Galilean satellites, they are, of course, already concentrating the salty component because the ocean is just a small fraction of all the H2O. Is it reasonable to be talking about several 8%?
Yeah, so it's a very good question. What we're sort of doing here is trying to put a maximum amount that what can be there. And even a small amount of potassium, if we're down into 0.2 or 0.3 mole percent rather than sort of at the upper end, that's still going to have an impact. But you're right, absolutely. We're looking at sort of the maximum amounts that we can put in. There is the thought that, yes, you can have most of the solutes in that fluid layer that are going to stay there, but you also have the rock layer. And at the higher temperatures, we think that we can get solutes from the rocks and dissolve them into the ice as well. So it's essentially, it's not as constrained as I would certainly like, yeah.